Hi, and welcome to the next lecture unit in the lecture chapter on nonlinear or kernelized support vector machines, which simply adds a couple of details on the polynomial kernel and explains how the hyperparameters of the polynomial kernel affect its decision boundary. So there is basically two versions, very similar versions of the polynomial kernel, the homogeneous one and the non-homogeneous one, with the non-homogeneous one being a little bit more useful, I would say, for practical application, which we'll see in a few minutes. So I'll start with the simpler formula. So the homogeneous polynomial kernel is defined as x transposed times x tilde and then to the dth power. So for that kernel, we can very simply check that an explicit feature map can be constructed like this here. And this formula contains all monomials of exactly ordered d. So let's walk through this formula here. So this is in the second part here, this is x1 to a certain power times x2 to a certain power times x3 to a certain power and so on, times xp to a certain power, so that all of these exponents here exactly add up to d. And then we have here this square root of such a multinomial coefficient in front of the whole thing, where we have d over exactly these k1, k2, k3, and so on numbers that occur also here in the exponents. And it's quite simple to check that this really is the explicit feature map of this kernel by simply, checking this fundamental property of our kernel function here, that it should be a shortcut for first the feature map and then the dot product computation. So I guess you can start from both sides. Guess maybe it's most simple to start from this side here. So you basically use your kernel function of this form, and then you simply calculate what comes out of this if you take this thing here to the dth power, and you use this multinomial formula here, which you hopefully have seen before, which kind of is an extension of the binomial formula, and that tells you how you can expand such a sum here to the dth power. And there you can also see where the the multinomial coefficient comes from. And this square root here comes simply from the fact that we have here not simply x1, but we always have x1 times x tilde 1 plus x2 times x tilde 2 and so on. And we already also considered before, but you could also simply check here that there are exactly these number of different monomials of exactly order d. So this would be the dimensionality of our feature map. We also discussed before that this becomes actually quite large if p goes up to a medium dimensionality, and d doesn't even have to be so large. And in that case, this kernel trick really saves us that we don't have to explicitly here calculate this feature map or feature expansion. We can also see that phi of x, or the feature map, does not contain any terms of lesser order. So for example, there's no linear effects in there. This is also the reason why I said this is maybe not that useful in practice, or less useful as the non-homogeneous polynomial kernel, which I'll introduce on the next slide. So here's an example for two features and for a degree of 2, and you can see how the explicit feature map now looks like, and you can see there's no effect in there with only x1 or only x2. So all of these here have exactly order 2. And generalization is this non-homogeneous polynomial kernel, which simply here contains this plus b. This is also how I introduced the general polynomial kernel in some of the lecture units before. It's more the general form that's being used. The maths is very, very similar as before, with a very similar feature map. So you basically, or the whole maths simply follows from, a certain consideration that we simply add a constant feature in the original feature space, which you could interpret as square root of b here. So this guy here you can also write like this, and now it kind of feels like as if our feature vector as x has a further constant element square root of b, and also x tilde has a further constant element of square root of b in there. And now if we, for this expanded version, apply the maths of the homogeneous polynomial kernel from before, you will, well, arrive with the same formula, but now you also have here this b in there, or square root of b I should say, also to the power of a certain exponent. And now these guys here, including this guy, kp plus 1, they all have to sum up to d, which means this kp plus 1 here, this guy can soak up certain powers, which in the homogeneous case would have needed to occur here as well, right? So for example, kp plus 1 could be, I don't know, d minus 1, and then you can only have here 1x1 in there, or 1x2 and 1x3, and all of the other variables wouldn't even occur. And again, by similar arguments as before, we can now simply figure out that this feature expansion here has p plus d over d dimensions. So it's basically this minus 1 here disappears, because as I've said, we have kind of now went from a p-dimensional input space to a p plus 1 dimensional original input space. And if we now write down the feature map here again for p equals 2 and d equals 2, it looks like this. And this now really looks quite useful for us. This really looks like the usual feature generation that we, for example, know from polynomial regression, where we have here squared effects in there, we have an interaction effect, and we have our linear effects and a constant term. We can also do a visual check of how the decision boundaries of such polynomial kernels look like. So I've here generated a linear decision boundary. So maybe I should also explain a little bit how the parameters are named here. So I guess degree is pretty intuitive. So that's the d. I'm actually using libSVM here. So that's a very, very popular support vector machine implementation, probably still the most popular one. This cof0 here is exactly my b. So I've set this here to 1. For the linear kernel, doesn't really matter. Here you can also see the classification error on the training set, and you can also see the classification error through cross-validation. On the left-hand side, I'm using a very simple data set that's basically, well, it's not really linearly separable, but the base decision boundary is basically a hyperplane. You can't do much better. And here on the right-hand side, I have a part of the very well-known spiral data set. And you can see here, if we simply use d equals 1, we simply have our soft margin linear support vector machine. Of course, for the spiral data set here, it doesn't work very well. So even for the training data set, we have a 50% error rate. Now we can increase the degree. So in this case here, I'm using degree equals 3. This, well, I guess we can say this already begins to overfit on the linear data set, or on the data situation on the left-hand side, where we would probably model with a hyperplane. On the right-hand side, it actually looks quite good. You can also see here that the training error goes considerably down. You're also not overfitting that much. Test errors is at least in the same vicinity as the training error. Again, watch out. I'm always using this non-homogeneous kernel here. And you will see in a couple of seconds that this really now makes a difference. Here it seems to work quite well. I'm now using, again, a non-homogeneous kernel, but now with degree equals 9 and for the left-hand side, and also probably for the right-hand side, we are now beginning to considerably overfit. You can see here the training error for the spiral goes down even more to about 5 or let's say 6%, the testing error stays the same. So this is a clear indication of overfitting now. And you can also see what I said before, that if you set this b here to 0 and you only use the homogeneous polynomial kernel, this might not work so well in practice. So here it doesn't really make a difference, but for the spiral thing, it doesn't work so well. And this is because all of these linear effects and these lower order effects that you usually need those, they are missing now.